would be same idea, only now instead of rho L, what do we have? We have rho S, it should have been S dy. Y'all follow me? Rho L is in what? Coulombs per meter squared times dy. dy is meters, so now rho L is rho S times dy. Can y'all follow me in that class? So this becomes rho S dy. Now I'm going to go ahead with this stuff. I'm going to say a rho right there is this over the magnitude of that. Right? So a rho is going to be, it's divided by rho. A rho is going to be x ax minus y ay, right, over that magnitude, square root of that, but there's another magnitude, so it's really over x squared plus y squared, and that would be the differential electric field right here. Please just try to get an idea. In electromagnetics, we always exploit symmetry. Remember, the infinite line ribbon, if you will, is coming out of the board. We know the electric field from a single line charge, right?
Yeah.
So make the line charge a little fat. That would be, it would be dy rho s would be the amount of charge on that infinite line, if you will. That would be the electric field at point of observation. Everybody with me, class? Y'all with me? Yes, sir.
Why is it x squared plus y squared?
That's x, that's y. Z is out of the board, right?
Yes.
That's why.
But it comes from, it's the magnitude of rho, it's the magnitude of rho vector times.
Here's rho, that's the square root of y squared plus x squared, right?
Yeah.
A rho would be what? Rho vector would be this over magnitude, which is square root of x squared plus y squared. Okay. So there's two square roots is just x squared plus y squared.
Oh, okay, yeah, I get it. Okay.
That's all it is. I see where you're going. He said, why isn't this times this?
Yeah.
Well, because square root times square root is root.
Well, I was just thinking, why is the magnitude, why is the power to the power
electric
of 1?
Field.
Yeah, no, I get it because rho is both the square root of x squared plus y squared, and there are two rows multiplied by each other, yeah.
Now it becomes simply x squared plus y squared, right?
Yeah.
Y'all good with that? And by the way, ask questions. If you don't see something, yell at me. Because it's better that we clear it up here. Usually if one person doesn't see it, it's more than one. And I could have made a mistake. Don't ever think I'm infallible. That's one thing that I never think. All right. Now if I look at that right there, I'm going to ask you something. Based on your gut feel for symmetry, what do you think is going to happen here? Come over here, same distance. Don't we have the same amount of charge?
Yeah.
All right. What happens to the components in the y direction, class? How many see they cancel? Now we could do the integration, evaluate it, but they cancel. And one thing about a good engineer in general in the field, they can see things where they can simplify. Cancellation of mathematics is a blessing to engineers. Mathematicians can do all they want with it, but we're talking about getting to the answer, not making a career of doing integrations. Y'all with me on this? So we can get rid of the y business. Good. It's gone. Now we got to do this. Now this kind of integration, I think you got. So if we take a look at E, it's going to be the integral of this, right? As a matter of fact, let me get the constants out in front. So I can take rho s over 2 pi epsilon naught, right? And I'm going to be integrating dy, so x is a constant, right? Correct, class? Take x out in front. Now I got the integration. This is in the ax direction. From minus a to a of 1 over the square root of x squared plus y squared dx. This looks like a natural log for some reason. But I'm actually, maybe. So in the back, what does he have? I mean, look in the back of the book, or we can do it where, in the back of the book, on page, what was it?
How did it become the square root?
It didn't. That's
okay.
I'm so sorry. It's x squared plus y squared. It's not the root. It's going to be 1 over the square root of this. The answer is going to have 1 over the square root of this. And if you look at the back of the book, 1 over x squared plus y squared integrated.
1 over y, inverse.
Inverse tan?
Or y.
Is what? What, I mean, are you going to what page?
600.
Yeah, it's 1 over a tan, inverse tan of x over a, right? Right, and this one, the integration with respect to y, so it's 1 over, I mean, let me do it this way. So this is equal to rho s x over 2 pi epsilon naught, and then over here, the evaluation of this integration is going to be 1 over x right here, and it's going to have a tan to the minus 1 of, and the way the book's going to have it is, it's going to be y over a, I mean y over x, yeah. It's evaluated from minus a to a, right?
Yep.
So, and this is for y going from there to there, so that's rho s over 2 pi epsilon naught. This x and this x cancel, so then I get the inverse tan of a over x minus tan of inverse tan of minus a over x, and that should be a plus there, so it looks like it's going to be rho s over pi epsilon naught, and it's going to be times tan minus 1 of a over x. Is that the answer? And that would be in volts per meter in the ax direction. Is that correct?
Are we integrating over y or x?
Why? But
We
the integral.
replaced a with y.
Oh, it says dx right
See,
there.
I'm sorry. In the book, the integral is done with dx in the.
Yeah, it says dx right there. I was confused.
It says dx, so he thought it was
dx.
Oh,
dx.
That's me. dy.
Okay. I was confused there.
I'm sorry. It is the. So is that the answer he has?
I'm not sure, but through trig, can you pull the negative through trig, just like trig stuff? Then that's how
The
you
what?
got it. You cancel the 2 because you.
I didn't cancel. I combined.
Yeah.
This you can take the minus a out and makes it plus.
Yeah, and it makes it plus, and then that cancels.
Doubles that.
Okay,
right.
that's what I was
What does he
making
have for the answer?
sure. I don't have it, so I'm not sure.
Which problem is this again?
Shit. 23.
3.23.
He gives you a value of rho s or not?
Yeah, he gives us stuff.
What does he give?
Actually, not for this problem. This is 3.23. He does not give us it. He does not give anything.
Doesn't give us rho s. Is this the answer?
Yeah, that's right. Yeah.
Okay. One thing I'm going to comment about this. Now, a lot of times I just put k down because k is 1 over 4 pi. But a lot of times you're going to see what Whitworth chooses for rho s will cancel the pi and the epsilon or something like that. So sometimes it's better just put it down as 1 over 4 pi epsilon or 1 over 2 pi epsilon. In the book, the classic way is to have this with a 2 pi epsilon naught instead of k over 2. Yep.
So, should we just memorize the, or like, learn the line and rivet and then surface charge?
Here's what you need to know, because he
Integration.
asked a very good question. Like, what should I be familiar with that I know I'm not going to be given? You're not going to be given the value of the electric field from an infinite line charge. That you have to know. You won't be given the value of the electric field from a point charge. You won't be given the value of the electric field from a loop. We did that one. I'll talk about these, right? You remember doing that? You won't be given the electric field from an infinite sheeted charge, which is the next part. Because now when you look at this, since we're on the topic, that ribbon right here, this is the electric field for the ribbon. I'm going to erase this stuff. It isn't. So if you look at this, and I've got a question for you, because you're going to see this. There's so many ways to do what I'm about, to get to the result I'm about to talk about. But I bet you can see that. So if that's the electric field, remember, it's the electric field for a sheet of charge of a given width, or a ribbon of charge. Now, two things you have to observe. If you're talking about the electric field from this finite ribbon right above the axis of symmetry, it's pointing away from the charge. It doesn't matter if that's y, x, or z, or if it's cocked like this. It's always pointing away. You all follow me on that, class? The second thing is, if you let a go to infinity, what happens? Well, what is the inverse tangent of infinity? Let's do it this way, so you understand what I'm talking about. I take a look at this, right? If this is phi, and this is y, and this is x, so tan of phi is equal to y over x. Y'all with me? All right. Well, when this right here goes to infinity, what does this go to?
90.
That's right. Pi over 2 radians, right? So if you look at this, when this goes to infinity, please watch. This becomes the electric field, and write this down from a sheet right here of charge, is really as A goes to infinity for this formula, it becomes simply equal to rho s. You'll notice this goes to pi over 2. The pi's cancel, right? So I get rho s, this is the magnitude, over 2 epsilon naught, and I call it the A normal direction. I want to talk about this for a second. I want to tell you, you'll appreciate this, because this makes things, it sort of gets down, makes it nice and easy to understand, not convoluted. So, if we have an infinite sheet, just assume it's here. Here's my infinite sheet. I can't draw an infinite sheet. And here's the origin. And this is an infinite sheet of charge. This has a value of rho s on it. So assume it's infinite. If you're above or below the plane is the only thing that determines whether it's plus or minus. The magnitude will always be just rho s over 2 epsilon naught. If you're above the plane, if this is positive z, if you're above the plane, it doesn't matter where you are above that plane. The electric field for an infinite sheet of charge will just be rho s over 2 epsilon naught in the normal direction. Normal is away from it would be az above it. Y'all see that? Y'all with me on this? Now if you're below it, what happens? Well, if I'm below it, same magnitude, right? The electric field down here is going to be rho s, whatever that is, over 2 epsilon naught, but it would be in the minus az direction. Y'all follow me? And that's really it. If it's a positive charge. If it's a negative charge sheet, then it'll be in the opposite. Then down here will be pointing at it, up here will be pointing down. Y'all with me, class? Something else I want to tell you. Some of these approximations you might not see why we talk about, but they're very useful in the real world. For instance, if you're talking about a very long wire that's suspended and you know it's conducted charge. Let me give you a little background. You know who Ben Franklin is?
Yeah.
Ben Franklin is one of the original signers of the Declaration. Do you know what I'm about to tell you about? So Ben Franklin's very, very well known for his first, he was the guy that did the initial work on lightning. My PhD was in late time electric field transients related to lightning. It was really about nuclear weapons, EMP from nuclear weapons. We can't publish it. So anyway, what happens is Ben Franklin knew that the reason lightning happens is because there's a lot of charge accumulated, negative charge, and the ground would induce positive, and it just causes what's called a step leader to happen. It's basically a breakdown of the atmosphere. The electric field gets larger than the breakdown stream of the atmosphere, and lightning's formed. You all see lightning all the time, right? So he knows there's charge, and he knows whenever there's negative charge, positive charge is induced. Clever man that he is, he knows, well, if I could some way find a way to get the amount of positive charge down here, it would repel itself. So here's what he did. He took, it's called Franklin belts. He had this long conducting rod, right? Then around the outer edge of it, not conducting, not touching, he had a bell, basically a bell, right? Then in there in the center, he had two things, but very thin but conducting pieces of, think of them as twine or something, only conducting. And they would attach these very, you might say they were metal pith balls that were hollow, all right, so they're light. And as that charge above there would come, their negative charge would induce positive charge on the ground. The positive charge would get on the pith balls. Now, likes repel, right? So it'd start pushing up. And they'd hit the bell. And the bell, it was set up so the bell was grounded to the earth. So when they hit, all the charge bleeds off and they go back. And they go back. And the closer that storm was, the faster those bells would ring. It's called Franklin bells. And it had to do with the amount of charge induced on really this rod he had up. There was never a key with a jar and a kite. Have you ever heard of that one? That didn't happen as far as I know. All right. I mean, if it did happen, God knows he'd be dead. But anyway, if you have just a long conducting wire above the ground and a thunderstorm comes, you can assume that there's going to be a charge induced on that wire. Doesn't matter how far off the ground it is, it will be induced. So how do you get an idea how much charge is induced? There's electric field meters that you can get. You can put them right near that thing so it looks like an infrared conductor, and you can measure the electric field, and because you know how far away you are from the conductor, you can estimate the charge density. And that charge density tells you a lot about the magnitude of the charge that induced it based on a lot of things. One last thing about a thunderstorm to make sure you understand. So, you all see thunderstorms, right? What causes a thunderstorm? Well, rain or grapple, which is basically slush, or hail, or something that is precipitating that has a charge on it. And you all know how, a balloon, you rub it on your head, you can stick it on a wall. Charge, when you have things that have, without getting into the details, they have a dielectric constant, and they have what's called the ability to frictionally get a surface charge, which rain does. When it's falling, it takes charge from the air, drops it onto the earth. It happens to be positive charge, usually. You got a negative charge center. So, where is the charge center? Well, the lower charge center is about 6 kilometers high. The upper charge center, y'all see cirrus clouds, the very tops are flat, usually they're called anvils on the top of these thunderstorms. That's roughly 10,000 feet. I mean, it'll vary somewhat depending on if you're at the equator or Alaska, stuff like this, but it's about right. There's a charge center up there that's positive. Negative, right at 6 kilometers, the ground has a positive charge. And what happens a lot of times is you get intercloud lightning that goes from the negative to the top one. That's the most common. Or you'll get cloud to ground. That's the most dangerous and also the one that's loudest. You'll hear that really, and you all know what I'm talking about. Cloud to ground from the charge center to that. But there's one other type of lightning event that's very rare. It's called the superbolt. It's when that positive charge center, this is weird. It's when you get super amounts of like tornadic activity and stuff like this, and you get shear. Then all of a sudden what happens is the positive charge center, instead of having a dipole vertically, it'll be the positive charge center over here, the negative here. The positive will induce a negative on the ground, and then you get something that's way up there. 10 kilometers, takes a lot to break down the dielectric and get that long of a bolt coming down. And the difference is that bolt can have 270 kiloamps of peak current and has a much longer duration. For the for the one that's just above you, the 6 kilometer one, the cloud to ground, 20 kiloamps is about the limit. But that one's the one, if you're in a glider or if you're in an aircraft, a small aircraft, that one can bring you down. And that's one of the things I'm just telling you from a long experience I've had with lightning.
What is the end goal of studying lightning? Do you plan on controlling the weather or like?
No. It's saving lives.
Okay.
If you want to know the truth, nobody's going to harness lightning and get energy. That's all fictional. But the big problem is when you're making a system like cell phones. I've worked with this. Cell phone towers, when they get struck by lightning back in the past, usually the lightning protection equipment it was protected by the stuff they were trying to protect. In other words, the wrong thing blew. Mm-hmm. And so they try to find ways to do lightning protection for any device that could be struck by that renders it safe. And I got a long list of stories about how bad people's perception of what lightning can do is. Matter of fact, I was working for Adtran. I went up there one time, not working, but I was working with Adtran, and we were looking at these cell phone towers. And they make lots of chips, tens of thousands, hundreds, and units too that go on these cell phone towers. Well, they kept on getting knocked out by lightning. Well, they had lightning protection equipment. The problem was, lightning protection equipment was designed for certain structures with certain a certain type of phenomenon, and I can't get into all this because they're surge impedance, and it was always the circuits they had that were getting blown. So I got up there, and you would think it wouldn't be hard to engineer that. It is. Okay. How about next one? You got one?
3.22.
Hope you don't mind some of these stories. I'm trying to at least give you some perception of how the stuff's used. What? Or
3.22.
22? Okay, which one is this?
Circular disc in the XY plane.
Okay, this is, again, we're going to use the building block of a loop for this one. You can almost see it on that. So we got a disc. It's in the XY plane, call that XY, and it's got a certain radius, right? I hope. Y'all with me? It's got a radius A. Is the charge density constant?
No, it's 12 rho.
Okay. This is a good one. So this has got charge on it, right? So all this has charge. It's got a charge density of rho S equals what?
12 rho Newton coulomb, or
Nanocoulomb.
nanonewtons per.
Nanocoulombs.
Sorry,
Nanocoulombs
coulombs
per meter squared.
Yeah, you're correct.
All right. Y'all with me? Centimeter? Oh, Wentworth. I hate that.
And then radius is 5 centimeters.
Is what?
Radius is 5 centimeters.
All right, so A is limited to 5 centimeters. This is me personally telling you, he wants the electric field on the z-axis from this one, okay? Now, here's what we're going to do. We're going to start, we're going to find, if we just had a small loop right here, I'm going to draw it, I'm going to show you what I mean. Right there, of a given distance rho, I want the electric field at a height z from that loop. So we did this one.
He says 20 centimeters.
What? Z is 20. Don't worry about that. We'll put that in one. You all with me, class? So I'm going to put it over here. We did the problem. If you just have a loop like so, call it X, Y, and Z, and I got a loop like so, of radius A, or radius rho. Let's do radius rho. And I'm up a distance Z. Then, remember me doing this for you? Remember we got the differential electric field from a chunk integrated one? How many remember what it is? The E field on the Z-axis from that was equal to what?
Rho L.
Over 2 epsilon naught, right? Times what? Times Z, right? Times
The radius, which would be rho.
A,
A or rho, yeah.
Yeah, we'll use rho, right? And then it's going to be over,
Rho squared plus z squared.
that's right, Z squared, right? Y'all follow me on this?
It's
3 halves power, that's it. 3 halves power, and it's in the AZ direction. Okay. Are y'all with me? So we proved that. Now, I expect you to know this, that one. So, maybe I'll put it down like this and start. You should know this one.
So we should know line,
Loop and,
well, line, sheet, loop, should we know ribbon?
no. I mean, that's a little involved, but you should know line, sheet. We're at a point, start with a point. Point of charge, right? Then a line of charge, a loop of charge, and an infinite sheet of charge. Now, from those things, by the way, you can usually use them as building blocks and find the electric field from anything else. All right, by integration, we'll do it.
So we just need to know the sheet, the line, the point, and the ring, and then we can compute everything else.
Almost everything, with few exceptions, assuming there's some level of symmetry.
Symmetrical, yeah.
And so I have that, right? You all agree with this?
Yep.
Now I'm going to say, well, I don't have quite rho L. I have, and Tom Schumpert used to say this as a professor that was here years ago, and he retired. If you have something that is d rho thick, the actual value of rho L is simply the charge density times d rho. Does that make sense to everybody? Charge density is always what? It's coulombs per meter, right? Rho L. All right, I'm sorry. Line charge density is going to be coulombs per meter. Surface charge density is coulombs per meter squared. When you multiply by d rho, which is meters, you get coulombs per meter. So I can come up here, and just bear with me, class. You see where I'm going with this, guys? I'm going to find, yeah.
Is this supposed to be in the cylindrical coordinate system?
Yeah, it is.
Oh,
Rho is cylindrical.
yeah.
I mean, the reason is you use the coordinate system that lends itself to symmetry for the problem you're doing, and that's not really an exact way of saying it, but if things are cylindrically symmetric, use cylinder coordinates. If they're, spherically symmetric, use spherical. That's the general way you do these things. Okay, now back to this. Now you see rho L, I put that down as rho S times what? Times d rho, right? This became rho S times d rho. But what is rho S?
It's a constant times rho.
Yeah, and here's where it gets fun. All right. Now Dr. Whitworth likes to put down things in terms of something per centimeter squared. I hate that. Always use MKS units. Take it to meters, meters squared. And I'm just telling you from personal experience. You can do it this way, but then epsilon is in farads per meter. Then you got to change epsilon to farads per centimeter. You got to do all this nonsense if you want to be correct. I hate it. I come over here and I say rho S is 12. Now, is rho measured in centimeters there?
Yeah. If you're talking about the thickness of the disc, it's also measured in centimeters. Yes.
Well, I mean, is the measure? No, it can't. But this has to be MK. The rho itself has to be measured in meters. Here, the units can be coulombs per centimeter squared. But I mean, all these formulas are based on MKS. Rho here and epsilon are MKS units. Farads per meter.
It says when rho is in centimeters, though.
Rho is in centimeters?
That's what it says. It says, consider a circular disc in the xy plane of radius 5 centimeters. Suppose the charge density of a function,
Oh
blah,
my
blah,
God,
blah.
that's it.
Rho s equals 12 rho nanocoulombs per centimeter squared when rho is in centimeters. Find the electric field intensity
Just
at a
put
point.
rho in terms of meters.
Okay.
Okay.
So, 1 centimeter is 10 to the minus 2 meters, right? Isn't that right?
Yeah.
Okay, so if that's in centimeters, in terms of meters, what would it be? 12, 10 to the minus 2 times rho, right? Now rho's in meters. Do y'all follow me? If that's centimeters, if I multiply 10 by 10 minus 2, it's meters. You agree with that?
No.
The rho, just the rho, not the units outside of it. Ready?
Okay.
You got me? Now what about the now we talk about the units. We have nanocoulombs per centimeter squared. We multiply that by what? 100 centimeter squared over 1 meter squared. Do you agree with that?
Yeah.
Follow me? What is that? That's 10 to the 4th nanocoulombs per meter squared. Nano is 10 to the minus 9th, so this is what? Really 10 microcoulombs per meter squared, right? 10 to the 4th times 10 to the minus, 10 to the minus 9th times 10 to the minus 4, or 10 to the 4th is going to be 10 to the minus 5th, right? Am I wrong? Wait a second. Nano is 9, 4 from 9, 5. That's right. That's 10 microcoulombs per meter squared. Do you agree with that, class? And nano is 10 to the minus 9th, right? So this is going to be 10 to the 4th. Do you agree with that? 10 to the 4th times 10 to the minus 9th
Oh, yeah, that makes sense.
is going to be what?
10 to the minus 5th, which is 10 micro.
10 microcoulombs per meter squared.
We're
Agreed?
going to then multiply the.
I'm not done yet, yeah.
Okay.
But that's the units. Then I got to take this crap. So then I say that rho s itself is going to be equal to 12 times 10 to the minus 2 times 10 to the minus 5th is really, I just put as 10 to the minus 7th.
Wait, I thought it was over 10 to the minus second.
Hold it, what?
I thought it was over 10 to the minus second. 12 over 10 to the minus.
This is in meters, or centimeters, right?
Yeah.
To convert that to meters, I have to multiply that by 10 to the minus 2, don't I?
Yeah, it's just, you have it as divided. Rho s, you said it says rho s is equal to 12 over 10 to the minus 2.
No, that's in brackets.
Oh,
is
that's
parentheses.
brackets, okay. Okay. That makes sense.
Sorry. All right, so just take a look at this. We got 12 times 10 to the minus 2, right? Then it's times 10 to the minus 5, right?
Yep.
So that's going to be 10 to the minus 7 times 12, or 1.2 times 10 to the minus 6. Agree with me? So this is 1.2 times 10 to the minus 6 coulombs per meter squared, but it's times rho. And now rho itself is in terms of meters. Boy, I like it. You all with me? He'll give you, by the way, epsilon in terms of farads per centimeter, and that's really going to be 8.854 times 10 to the minus 14. I think he does the problem that way in the book.
He does.
I hate it. I mean, because I tell you, it's real easy to mess up. Real easy. So, anyway, coming back to here, now I'm going to replace ds in here by that, which is 1.2 times 10 to the minus 6 times rho. So you can see this becomes now dE here becomes 1.2 times 10 to the minus 6 times rho, but there's another rho, so I just make this rho squared, okay? Can y'all follow me in that, class? I had a rho here, right? So I had a rho over there, so rho squared. That's all I'm doing. Y'all with me, class? Now I need the electric field. I got to do the integration. So let's do it. Let's do it right here. So to get the electric field on the z-axis, help me out with this one too. I want the constants out in front. So z is a constant of 1.2 times 10 to the minus 6 divided by 2 epsilon naught. I'm going to leave epsilon naught the way I like it, MKS. Then I have z out in front, right? Then I have to integrate. It's in the AZ direction, by the way. Then I have to integrate from 0 out to the radius of 5 centimeters, or really it's going to be 0.05 meters. Do y'all agree with that, class? And it's going to be rho squared over rho squared plus z squared to the 3/2 power d rho. You agree with that? Now that integration's in the back of the book. Let's see. Can we do a quickie on that? That looks like that looks like something over the square root. You got, what is it? Rho over the square root of rho, something like that. That one I don't know off the top of my
I
head.
didn't see it in the back of the book.
Well, I should.
I've seen integral tables with that before, though.
Oh, there's plenty of them. We can do it probably. Let's see this. First, we didn't make a mistake, did we?
No, that's right. I remember looking at the solution, and that's where he got
Does
it.
he have the solution in?
He definitely does. I don't.
Let me just try this. All right, so we gotta do
Do
this.
separate integrals?
Huh?
Oh, I think he did. Yeah, he did.
Squared, and then do dp over the.
Say what?
You would have the integral of rho squared, and then you would have another integral of
Integration by parts.
1 over rho squared plus c squared raised to the 3/2.
Yeah, he does it by parts in his solution.
You can do it by parts if you want.
And then you just multiply them back together.
Yeah, you can, but honestly, I'd mess with this. So you can do it by parts. It's the easier way.
It's a lot easier.
Can use trig, can you?
The easier way is just put on
Yeah.
symbolic integration.
You just do.
What does it come down to, by the way? Say again?
So throw it into MATLAB or something.
Yeah, if I had to do this, seriously, integration by parts would make sense. You would have u, v, and then if you look at this, if you have just rho over that, you can put u equals rho squared plus c squared, and then du would be just rho d rho, and you can get it that way if you want to mess with it. I don't want to waste time on this right now because I'm trying to get something else. So what does it come down to is all this stuff? Class?
Got it pulled up, but it's a lot. It's this equation right here. That's his answer. He gets,
Where?
This is what we have here. It's this guy.
Yeah.
He goes down. This is his answer.
Yeah, he uses UDV.
He does both parts. Yeah.
Yeah, but that's not that bad. He's got natural log, he's got stuff in front of it. All right, I'm just gonna move on to the next one on that one, but that's how you do that.
Okay. Cool.
Okay. Normally, if it's a constant, it's an easy one, because if it's a constant, then you don't get a rho squared here. If it's charge density is constant, you get rho over rho squared plus e squared to the 3 halves, and you'll let u be equal to rho squared plus e squared. du is gonna be 2 rho d rho, and you got, if this was rho, you would have the differential. You can do it, but don't worry about that.
Would you give us an integral table for something like that?
Absolutely.
Okay.
I wouldn't expect you to do crazy integrals. I'm not at this level. If you're a PhD student and we're doing theoretical electromagnetics, yeah, but we're not. This is, I mean, frankly, in the real world, I can't imagine anybody struggling with that. They would look it up on the table or use calculators or math get or something. Seriously. All right, what else have we got?
I'm good.
Yeah. I think,
Nothing else?
Yeah, I think I'm good. Question was.
Okay, so now, my time. Fine.
You have 10 minutes.
Huh? I got 10 minutes, right? At least.
Yeah, you do.
Maybe at least 20. Go ahead, take 30. I had one professor. Actually, he didn't do it to me, but in graduate courses, this guy's from Germany. His name was Feuchtwanger. He was a Jewish guy in Germany, and he fought in Israeli 68 wars. He was more German than anybody I remember. Anyway, in his attitude. So he would always go 15 minutes over the lecture. So the kids in this, and this is for graduate courses in physics, very smart theoretical, but they turn the clock ahead by 15 minutes. And he'd get in there and okay. Then he figured it out. Then oh man, don't ever get something like that mad.
Is there any way you could do this last problem with dq being rho s, d rho? This problem here, is there any way you could do it with the dq being equal to rho s, d rho, d phi?
Yeah, but you're asking for another integration, then you have to do a d-phi integration.
Okay.
You can take a simple chunk of charge that's got it's got 2 dimensions of differential, d rho, and then you would have rho d phi, the other direction, all right, times rho s. But then you're going to have to do the phi integration,
Yeah.
which is a pain.
Yeah.
I mean,
I just didn't know if it was possible.
it's just going to come out. When you do the phi integration, you just get 2 pi. That's it. All right, now back to where I'm trying to go about with this. We talked about cylindrical, spherical, and Cartesian coordinates. We did the standard infinite line, infinite surface, loop of charge, right? We did a disk, we did a point charge. So now, after that, I mean, it's nothing but fun. I'll give you some products, but now volume charge. For the most part, volume charge, only thing you can do that's solvable is really symmetric volume charge densities. I'm just going to mention one without spending a whole lot of time. Please just watch this and it'll make sense. So, what if I had, and I got to tell you this, if you had a sphere of a given radius A, and this is important what I'm about to tell you, it's centered at the origin, and the sphere had a charge density rho s. This is a sphere. And I wanted to know the electric field anywhere inside the sphere, it will be 0 if it's symmetrically distributed. That I can promise you. And we're going to learn that from Gauss's law. But if you're outside the sphere, if I'm at a distance, call it r, where r is greater than a, then the electric field out here will be in the radial direction. So it's going to be in the AR direction. And its magnitude would be as if all this charge was centered at the origin. You all hear me? This is a spherically symmetric charge distribution. The electric field will only be, in magnitude, only be a function of the distance away. So you can take all that charge, stick it at the origin, So what's the surface, I mean, what's the amount of charge, what's the surface area of the sphere? You need to know this one. The volume is 4/3 pi r cubed, right? But the, that's right, you gotta know that. So it's 4 pi, in this case I put a squared times rho s, and then you divide by 4 pi epsilon naught, and it's going to be divided by r squared if you're outside. 4 pi's canceled, that will always give you the electric field strength for a sphere that's infinite. Now, if the sphere has some, suppose instead of just the shell, it's a solid piece of, it's solid, and you have a charge density that varies versus r, but symmetric otherwise, then you would take this shell, and you would say it would be rho v, the volume charge density, times d rho, set that equal to ds. Do you all with me, class? Or let's say it equal to d cubed. In other words, this right here, we'd put a differential thickness. We'd assume this thing now has a thickness, call it d rho. Y'all with me? Now instead of a surface charge density, assume you have a volume charge density, rho v. It's spherically symmetric. Y'all with me, class? Now the charge that was this, now this charge would become, well, it would be equal to 4 pi r squared, that's the surface area, times d rho, or times dr, and then it would be times the volume charge density, and this would be the differential electric field. Can you all see this? I'm going to create a differential electric field from that spherical surface of a given thickness, then you would integrate that over the thickness to find the total electric field. You all follow me on that? That's a very classic problem. It's a good one too. I'm just showing you this. I don't remember if he has it in his book or not, but that's a classic problem. So now we're basically done with the basic electrostatics. Now I'm going to show you something that makes life so much easier. Remember, all the stuff we were doing are vector-based, right? Differential electric fields with vector components. You've got to integrate. Hopefully there's an axis of symmetry that we can exploit to get the end result. Now we're going to use Gauss's law. How many have heard of Gauss? How many know what Gauss's law is related to electromagnetics?
Somewhat remember it, but
I am on a lot of things. Kind of remember. Well, let's see. Can't put a pencil in his hair for unless it's a movie.
if you ask me to write it down right now, I could definitely not do that.
All right, so Gauss is, one thing about Gauss I love.
Netflix is.
You know, Gauss is a guy from, I don't know, 300 or 400 years ago. But Gauss is a real genius. He was my hero when I was a young kid. Here's why. I hated doing repetitive things that they gave us in school. I went to a Catholic grade school. One of the things they do, if they wanted some time to grade papers, they'd ask you to do something stupid, like add all the numbers from 1 to 100. Do you all know this one? From 1 to 1,000, or 1 to 1,000,000, or 1 to 50 or something. It takes a lot. Kids would do it. So what Gauss did is, he had to do that. He was in like 2nd or 3rd grade. Take the numbers 0, blah, 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 100. Then right below that, 100, blah, blah, 0. Add them up. 100, 100, 100, 100 and 0 is 100. 1 and 99 is 100. 2, so he gets 101, 100. So he knows how to multiply. He gets 10,100. He divides it by 2. 50,050. Comes up in a few seconds, literally in under a minute probably, shows the teacher. How'd you get that? Shows her. She's dumbfounded. Took her to the university. He skipped a lot of grades. Basically, that's the kind of savant that he was. And he was a brilliant, brilliant guy. He had all sorts of stuff from him. Unbelievable insight. Einstein and stuff like this with modern day, you know, they were into the bizarre abstract world of physics with what they could imagine. But these guys are classical mathematicians. So Gauss's law says this. Gauss is a very smart guy. He's the guy that came up with this. He's a physicist too, very familiar with the physics of the time. And he found out one thing, that if you have a charge, any kind of a charge, if you do an integral of d dot ds over the closed surface, that indicates a closed surface, you will find the charge enclosed. Now that's an act of brilliance. That's called the integral form of Gauss's law. if you use Stokes' theorem, do you know what Stokes' theorem is? You don't have to, but Stokes' theorem would say that if I take the divergence of that dV, or I take the integral of divergence of d right here, dV over the total volume, pardon me, the volume enclosed by that surface, I would also get the charge, Q enclosed. As a matter of fact, this right here, if you think about it, if that's the charge enclosed and I'm integrating over the volume, that's the volume charge density. So that means when you talk about the volume charge density, it's equal to the divergence of D. Do you remember that at all? No? All right, I mean, you can see it that this is a mathematical theorem. I'm out of time basically, but it's a mathematical theorem. It's using Stokes' law. Integral of a mathematical function f over a surface, defined surface that's closed, it has to be closed, is equal to the divergence of that integrated over the volume. Now, if you're talking about that's the charge enclosed, then divergence has to be the charge density. Or else it doesn't make any sense. Charge density would be in coulombs per meter cubed. You all with me on this? Back to this form. So here's where you can use that to exploit symmetry. Now y'all remember in physics you heard of Gauss's law, right? Well, the classic problem your instructor probably did is say, well, let's see how it works. If we just put a charge Q at the center, and we don't know anything more than Gauss's law and that we can exploit symmetry. Well, if I come out a distance r from there, does everybody, you have to be able to see this. Do you agree, oh, I didn't say what the D field was. The D field itself is like the E field. It's equal to epsilon times the E field. That's all it is. Y'all, okay? Now, they're proportional. They're proportional with this constant epsilon. So, you all agree that common sense says if I have a charge, it doesn't matter if I'm going this direction, the magnitude of the electric field will only be a function of the radial distance away. But you already know that, right? You know it's what? It's Q over 4 pi epsilon naught r squared AR. You know that. That is Coulomb. It's basically it's Coulomb's law. Coulomb's law. So, you can get that from that law too. So if I come around here, I have a surface S, and it's closed. I know the integral of d dot ds over the closed surface is the charge enclosed. Well, we just talked about it. The closed surface has a surface area of 4 pi r squared, right? When you do a dot product of a vector, if you have the D field itself dotted into the vector, the surface vector, and I talked about this last time, the differential surface vector would be equal to r squared sine of theta, d theta, d phi, and it would be in the AR direction. When you dot these two, you're only going to get the D field's magnitude times that surface area, and when you integrate, you find out that Q is equal to 4 pi r squared times the D field. And that's the component of the D field in the R direction, but that's the only one. You can see, therefore, that the D field is equal to simply Q over 4 pi r squared. And if that's the D field, if you divide that by epsilon, you get the E field. You all see this, class? And that is Gauss's law applied to the simplest problem. Now, what happens with a line charge before I let you go? What do you think happens? Got an infinite line charge, right? On the z-axis. Now, what we're going to talk about, and I'll tell you, is if you can place a surface around there that can exploit symmetry. So a surface that can be used to exploit symmetry. Let me show you what I'm talking about. Y'all agree for this thing, if it's an infinite line charge, cylindrical symmetry makes sense, right? So if we put a symmetric surface here that's centered about the z-axis and has a radius of rho, not drawn, right? And we'll always leave the height of this symmetric surface to be 1 if possible. Then I can say all the charge in that surface is equal to the D field integrated over, or within that surface is the integral of the D field, right? Now, you have to be able to see this. So if it's an infinite line charge, you all agree that the D field has to be radially away. If it's infinite symmetric, right? If rho S or rho L is on the axis and it doesn't change versus any position, then the D field has to be out. For any charge here, I got a charge, same magnitude here, and it'll cancel the vertical components. Do you all agree with that? So if that's in that direction, now just look at this. Here's the surface. The only thing that D dot ds only thing that will actually in any way contribute to that integration will be the radial D field right here and the surface area. So again, integral of D dot ds over the closed surface is the charge enclosed, right? Charge enclosed is H times rho S, or rho L, pardon. If H is 1, it's just equal to rho L. Can you all appreciate that? That's the amount of charge in this thing. It's a little pillbox. Think of a tuna can, all right? Now, that's equal to what? The integral of D dot ds. That's the what? The outer edge of this tuna can, right? The label. That's going to be the perimeter or circumference, which is 2 pi rho, right? 2 pi. It's cylindrical, so it's rho. 2 pi rho times d rho. And you can see here that d rho, therefore, is equal to rho L over 2 pi rho in the a rho direction. And if that's the D field's divided by epsilon. You remember we just got this result? Class? Do y'all remember that from an infinite line charge? That would be now the E field, right? This would be the E field, not the D field. Just dividing that by epsilon. You're going to see on Monday, we can apply Gauss's laws to all sorts of problems that make the answer obvious by exploiting symmetry. And it's really nice because you don't have to do any of these crazy integrals. I don't have a x squared over the x squared plus a squared to the 3 halves dx kind of integrals. It saves me a lot of aches and pains. Can you all see this class? Okay, on Monday a quiz. Quiz is going to be related to last homework, current homework. Okay? Please do the homework I assigned, past and current. Okay, if you got questions, I'm here to answer. Sorry I took so long. My morning random class, I ran over. Y'all get something out of this? You did?